we can approximate a function f of x using simpler functions. So that will be some constant multiplied by a function g naught of x plus another constant by g1 of x, and so on, up to some function gn of x. So given a continuous function f on the closed interval from a to b, so this function is in the inner product space of continuous functions on this closed interval, and we want to find the best possible approximation to f using functions from a specified subspace of this inner product space. So the error to the approximation at a particular point in that interval is the absolute value of the difference of f of x minus g of x. So that will be this distance over here at the specific point x. And we want to choose an error measure such as the total error, which is a difference between the areas of both graphs. So instead, we can integrate from a to b with respect to x, and that'll give us a total error in terms of the area between those curves. Now, given the mean squared error is more compatible with inner product spaces, we can choose this as our error measure instead. So what we can do is integrate from a to b, and our integrand is f of x minus g of x squared. And that's integrated with respect to x. So noting the inner product between a function f and g, and we take our functions as vectors. So this inner product, defined on this inner product space of continuous functions on a closed interval from a to b, is equal to the integral from a to b of f of x by g of x with respect to x. So noting the squared norm of a function is equal to the inner product between a function and itself, so therefore the squared norm of the difference between the functions is equal to the inner product of f minus g with itself, and therefore this integrand in the inner product becomes f minus g by f minus g, which gives the mean squared error. Recall that our least squares approximation to a vector from a given subspace is the orthogonal projection of this vector on that subspace, which we've seen previously. So if our subspace S is a finite dimensional subspace, of an inner product space V, and B is a vector in V, then the orthogonal projection of the vector B onto that subspace, which geometrically is this vector, is the best approximation to B from S. So in other words, the norm of B minus the projection of B onto S, which is the magnitude of this error vector, is less than the norm of B minus any other vector s in that subspace. So we can extend this concept to functions. So given a continuous function on the closed interval ab, and this function is in the vector space of continuous functions on that interval. And if we let this inner product space have the following inner product, so that's equal to the integral from a to b of f of x by g of x with respect to x. And if we let S be a finite dimensional subspace of the inner product space of continuous functions on a to b, then our problem involves finding a function g in the subspace S that minimizes the mean squared error. So that will be the squared norm of the difference between those two functions. So you can see the analogies to our least squares problem. So this squared norm is obtained using the inner product. So we have the integral of f of x minus g of x multiplied by f of x minus g of x integrated with respect to x. So note that we can view functions as vectors with a single component. So given that the squared norm and the norm are both minimized by the same function g, then basically we're looking for a function g in a particular subspace of functions that is closest to f. So therefore the projection of f onto the subspace S is the function g. So this function g is the least squares approximation to f from the subspace S. So recalling that a function g from a subspace of functions S that gives the best approximation to f, which is a continuous function on the closed interval from a to b, is equal to the projection of f onto the subspace S. And in our case here, our subspace S is going to be the inner product space of trigonometric polynomials of order n or less. So these polynomials are a linear combination of elementary trigonometric functions. So we have g of x is some constant plus c1 by cosine of x plus another constant by the cosine of 2 by x, and so on up to cn by the cosine of n by x, plus another constant d1 by sine of x, plus d2 by sine 2x, and so on up to dn by the sine of n by x. So this polynomial is of order n if the constant cn is not equal to 0 or dn is not equal to 0. So you may recognize this as a Fourier series. So we can write this as the constant c0 plus the sum of I equals 1 to n of Cn by cosine nx plus dn by sine nx. So effectively, the trig polynomials are the various possible linear combinations of 1, cosine x, cosine 2x, and so on to cosine nx, and also sine x, sine 2x, and so on, up to sine nx. So you can show that these 2n plus 1 functions are linearly independent and form a basis for a 2n plus 1 dimensional subspace of the inner product space of continuous functions on the closed interval from a to b. So one way to check if these vectors form a basis for this subspace is to check if they're orthogonal. So if that's true, then they'll be linearly independent and span this subspace. And that can be done using the definition of the inner product. So recall that was the integral from a to b of the product of two functions with respect to x. And if this is 0 for all combinations of these functions, then they form a basis for s. Let's now summarize our function approximation problem. So we wanted to find a least squares approximation of a continuous function f of x, and what we'll do is find the approximation to this continuous function over the interval from 0 to 2 pi. And we're going to make this approximation by a trig polynomial which we call g of x, and this trig polynomial is going to have an order of n or less. So as we mentioned, the least squares approximation of a function f from the subspace S is the orthogonal projection of our function onto the subspace S. So to be able to compute this orthogonal projection, we want to find an orthonormal basis being the set of vectors g0, g1, up to g subscript 2n. So remember that the subspace S is a 2n plus 1 dimensional subspace. So once we find this orthonormal basis, we can compute this orthogonal projection of f onto S using the inner product. So we basically take the inner product of f with each basis vector and multiply that by the basis vector, as we've seen. And recall, because this is an orthonormal basis, we don't need to divide this by the squared norm of each basis vector. So essentially the orthogonal projection of f onto the subspace S is the sum of the projections of f onto each orthonormal basis vector. So that continues on and on up to the orthogonal projection of f onto the basis vector 2n. So recall our trig polynomial was a linear combination of the following basis vectors. So 1 cosine x, cosine 2x, and so on, up to cosine nx, and sine x, sine 2x, and so on, up to sine nx, where n is a positive integer. So if we applied the Gram-Schmidt process to find an orthonormal basis for S from these basis vectors, so this orthonormal basis would be found relative to the inner product that we defined in our inner product space of continuous functions. So this inner product is defined on the closed interval from 0 to 2 pi. So we have the integral of the product of two functions from the inner product space with respect to x. So by taking pairs of these vectors, you can verify that the inner product is going to evaluate to 0 because you're going to get sine and cosine terms in the result, and sine of 0 on 2 pi is 0, and cosine of 0 on 2 pi is equal to 1. So the cosines will also be eliminated. So this inner product will be 0 for all combinations of these basis vectors. And therefore, given the vectors are already orthogonal, the Gram-Schmidt process will just normalize them to obtain an orthonormal basis. So for example, recall that the norm of a vector is equal to the square root of the inner product of that vector with itself. So here we have the inner product being the integral from 0 to 2 pi, and we have f of x by f of x integrated with respect to x. And I'll let you verify that this will evaluate to root 2 pi for the basis vector g0, which has the component 1, and root pi for all the other basis vectors. So therefore the orthonormal basis vectors we end up with are g0 is 1 on root 2 pi, g1 as cosine x on root pi, and so on up to gn being 1 on root pi, cosine nx, and similarly you'll have gn plus 1 being sine x on root pi, and this continues on and on to g to n, which is 1 on root pi by sine nx. So this here is our orthonormal basis for our subspace S of trig polynomials on the interval from 0 to 2 pi. So therefore, we can now compute this projection, or least squares approximation, to our function f. And now using our basis vectors, we can rewrite this projection as the inner product between f and g0 by g0 plus the inner product between f and g1 by g1, and so on. So we have the inner product between f and gn multiply by gn, which is 1 over root pi cosine nx, and the next term will be the inner product between f and gn plus 1, multiply by sine x on root pi, and this continues on and on up to the inner product between f and g to n, multiply by g to n, which is 1 on root pi by sine nx. So this here is the projection of f onto S. And now we can write this projection as a constant a0 plus a1 by cosine x, and so on up to an by cosine nx, and then we have b1 by sine x, and so on up to bn sine nx. So you can see this is a Fourier series, with a and b being the Fourier coefficients. So we can compute the Fourier coefficients as follows. So for example, this is a0. So a0 is the inner product between f and g0. So we have the integral of f of x by the basis vector g0, which is 1 on root 2 pi, and it's integrated over x, and we multiply this inner product by 1 on root 2 pi. So what you'd get is 1 on 2 pi by the integral of f of x with respect to x. And let's do another one. So for example, this term over here. So we have an being the integral of 0 to 2 pi. So we have the inner product between f of x and gn, which is 1 on root pi by cosine nx, integrated over x, and we multiply this by 1 on root pi. So this here is our coefficient an, as we can see. So if we evaluate this, we'd get 1 on pi outside the integral, and the integral of f of x by cosine nx with respect to x. And as an exercise, you can do the same for b1. So the coefficient b1 is this inner product multiplied by 1 on root pi. And as an exercise, also do the same for bn. And if you do that, we can write a0 as 1 on 2 pi by the integral of f of x with respect to x, and the coefficients a1 to an can generally be written as 1 on pi by the integral of f of x by the cosine of nx with respect to x, and we can write the bn coefficients as 1 on pi by the integral of f of x by sine nx over x. So again, a0, a1 up to an, and b1 up to bn, are the Fourier coefficients of our function f. So in general, this here is the least squares approximation to f using our trig polynomial. So let me just remove this now. So in general, this is the approximation to our function f using a Fourier series. I will make this more clear in an example problem. Let's find the least squares approximation to a function f of x equals x on the closed interval from 0 to 2 pi using a trigonometric polynomial. So recall our trigonometric polynomial is written in terms of the Fourier coefficients and trigonometric functions. So we had a0 plus a1 by cosine x plus a2 by cosine 2x and so on to an cosine nx, and the next term is the coefficient b1 by sine x plus b2 by sine 2x and so on up to bn sine nx. And the Fourier coefficient a0 was 1 on 2 pi by the integral of our function, which is x in this case, with respect to x, from 0 to 2 pi. So evaluating the integral, we have 1 on 2 pi by x squared on 2, evaluated from 0 to 2 pi. So what we get is 2 pi squared on 2 by 2 pi, which is 2 pi on 2, or pi. And the Fourier coefficients from a1 to an can be obtained using the following integral, which is 1 on pi by the integral from 0 to 2 pi of f of x by cosine nx integrated over x. So here we can use integration by parts. So we can set u equal to x, and therefore du is equal to dx, and dv is cosine nx dx. So therefore v is 1 on n by sine nx. So therefore this integral can be rewritten as u multiplied by v, which is 1 on n by x by sine nx, evaluated from 0 to 2 pi, minus the integral of v du. So that would be 1 on n outside the integral, and we have sine nx integrated with respect to x from 0 to 2 pi. So what we get is 2 pi on n by sine 2 pi n, and then we have minus 1 on n by 0, so that's 0, and minus 1 on n by minus 1 on n cosine nx, evaluated from 0 to 2 pi. So sine 2 pi by an integer is 0 for all n, so that's 0, And for the second term, we have minus 1 on n. By minus 1 on n, cosine 2 pi n. And minus 1 on n by cosine 0 is 1. So cosine of 2 pi by n is 1 for all the positive integers n. So we get minus 1 on n plus 1 on n is 0. And therefore this integral evaluates to 0. So our trig polynomial does not have any cosine terms. And now if we do the same thing to get the sine terms, so Bn is 1 on pi by the integral from 0 to 2 pi, and we're integrating f of x by sine nx with respect to x. So as an exercise, I'll let you evaluate this using integration by parts, as we did for the an terms, and that'll give you minus 2 on n. So b1 is minus 2 on 1, which is minus 2. b2 is minus 2 on 2, which is minus 1. And bn is minus 2 on n. So now let's get rid of this and plot our function. So here we can see our function f of x equals x in red, and in green we have a trig polynomial of order n equals 1. So that will be pi minus 2 sine x. And then in dark blue here, we have n equals 2. So that includes another term. And then we have a trig polynomial of order 15. So as we can see, the more terms we include in a polynomial, the better our approximation is. And the smaller the mean squared error or least squares error will be. So as we can see, at the endpoints, we get a bad approximation because sine of 0 is 0 and sine of multiples of 2 pi is also 0. So therefore, we get a value of pi on the vertical axes at these endpoints.